Hello everyone, this is another video on this one is on statistical mechanics. So we'll be solving previous year questions of statistical mechanics. Alright, so yeah, let's write some questions and try to solve them. Okay, so write down. These are mainly just previous year questions. Okay. So first question is a monoatomic gas consists of consists of atoms with two internal energy levels, two internal energy levels, ground state E naught is equal to 0, and an excited state E1 is equal to E. Specific heat of the gases. The specific heat of the gas is, see, a monoatomic gas consists of atoms with two internal energy levels. Okay, this is one energy level E is equal to 0. Another energy level E1 is equal to 1. E. Specific heat CE or C is asked. Okay, specific heat is asked. Yeah. So how to calculate it? First of all, what we will calculate? Uh, Average energy. Okay, that is summation I G I E I e to the power minus beta E I divided by summation I G I e to the power minus beta E I. Okay, so that will be um, 0 plus EI E1 in e to the power minus beta E1 divided by 1 plus e to the power minus beta E1. Okay, that is your what? That is your energy. Or E1 is E, right? Average energy. So now this was the average energy is E1 is E by 1 plus e to the power minus beta E. Okay. Okay, now total energy is what? What is total energy? Total energy is, to see monoatomic gas, total energy will be E will be, okay, this is suppose E dash. Total energy E will be, total average energy will be 3 by 2 kBT plus E dash. Okay, so 3 by 2 kBT plus E by 1 plus e to the power minus beta E. Beta means by kBT, 1 by kBT, 1 by kBT. Okay, so specific heat we know is CD is equal to d by dt of E. Okay, so d by dt of this one 3 by 2 kBT plus E by 1 plus e to the power minus E by kBT. Okay, so I will write it again, d by dt of 3 by 2 kBT plus E by 1 plus e to the power minus E by kBT. So 3 by 2 kB plus E goes out, dy dt of 1 by 1 plus e to the power minus e by kbt 3 by 2 kb plus e into this is 1 plus e to the minus e by kbt whole square minus e by kb. Okay, so this becomes 3 by 2 kb minus e square by kb over into 1 plus e to the minus e by kbt. And there is, I think I missed something here, e to the minus e by kbt also. And, okay, and also t square will be, I think there. Okay, I made a mistake. 3 by 2 kb plus uh, e by t 1 by 1 plus e to the power minus e by kbt 3 by 2 kb plus e 1 plus e to the power minus e by kbt whole square minus will be there, then minus e by kb into minus e by kbt into minus 1 by t square. See how many minus are there? 1, 2, 3, 4, 4 minus that will be to be plus eventually plus e square by kb t square into the power minus e by kbt 1 plus e to the minus e by kbt whole square. Alright, and that is the answer. This is the answer for specific heat. Right? This is the answer for your specific heat. Okay, next question. This question was from GS 2014. Okay, next is a good one. Okay. Consider a particle at three possible spin states. This is equal to 0 and plus or minus 1. There is a magnetic field. There is a magnetic field H present, and the energy for the spin states S H minus Hs. Okay. The system is at a temperature. The system is at a temperature T. So, how much is entropy? How much is entropy? Okay. So this is the question. Consider a particle with three spin states. S is equal to 0, S is equal to plus or minus 1. There is a magnetic field H present, and what? And the energy will spin states is S and S minus H. Its system is at a temperature T, right? Spin is 0 plus or minus 1. Energy for the states is minus Hs. That means what? That means energy will be, I will write, for S is equal to 1, the energy is minus Hs. For S is equal to 0, it is 0. For S is equal to minus 1, it is plus Hs. Right? Yeah? Okay. So the partition function we can write down here. Summation I gi e to the power minus beta ei. So everything has degeneracy 1. So 1 plus e to the power minus e to the power beta h is e to the power minus beta h. Okay. So here, how to calculate entropy? If suppose you have only Z, how to get entropy? You have to first find out the free energy. Free energy is minus kBT ln Z. After finding free energy, your entropy can be simply calculated as minus del F by del T at constant value. Okay. So let's do the F. F is minus kBT ln 1 plus e to the power beta hs plus 1 plus beta minus beta hs. Okay. And now entropy will be minus del F by del T minus kBT ln 1 plus e to the power beta hs and then is that alright? Now kV comes out, so del by del T of T, that is ln 1 plus e to the power beta hs to minus beta hs plus T whole into del by del T of ln 1 plus e to the power beta by kBT, sorry, hs by kBT e to the power minus hs by kBT kV ln 1 plus e beta hs T. This is 1 by 1 plus hs by kBT e to the minus hs by kBT. Take the derivative and hs by kV e to the power hs by kBT minus hs by kV e to the power minus hs by kBT. Okay. Okay. So now if you analyze a bit, um, the question is at low temperature, system is at temperature T. So at low temperature what happens is, at low temperature T what happens, e to the minus hs by kBt is very small. Okay, because T is tends to 0, so e to the minus hs by kBt tends to the minus infinity, that is equal to 0. So it's very small, right? And e to the power hs by kBt becomes what? E to the power infinity, which is very large. Okay, so again I ignore this term. I can like use this term. So that will give me S is equal to kb ln e to the power hs by kBt, right, plus hs by t e to the power, okay, hs by t minus, in the upper part it was only hs by kBt divided by e to the power um, hs by kBt also in the denominator part. So this cancel out become 1. Okay, this is giving minus 1. So S is equal to kb ln hs by kBt minus Just by t. Okay, alright, which is by t. Mm. Yeah. So for entropy is equal to 0, what happens if entropy is 0? Kbln hs by kBt is equal to hs by t. If you take it here, hs by kBt. Alright. So hs by kBt is e to the power hs by kBt. Okay. Yeah. So what happens here is um, here if t is infinity, this term becomes 0 and this term becomes 0. It's one. So t is not infinity. So t can, if t is 0, arrows, then also it's not possible. So I think entropy will be this term only. We don't need to do anything further. This is the entropy final expression. Okay. Yeah. Question number 3. Consider a system of so 2n non-interacting spin-off particles, each fixed each fixed in position and carrying a magnetic moment mu. Carrying a magnetic moment mu. Okay. The system is immersed the system is immersed in uniform magnetic field. A uniform magnetic field B. Number of spin of particles for which the entropy of the system will be maximum. Entropy of the system will be maximum is. Okay. Scheme in JEST 2014. Consider a system of 2 100 spin of particles, each fixed in position, carrying a magnetic moment mu. System is immersed in a uniform magnetic field B. The number of spin of particles for which the entropy of the system will be maximum. System is immersed in a uniform magnetic field B. Number of spin of particles. Okay. So let N1 and N2 what be the number of, for example, N1 be the spin of, N2 be the spin down particle. N1 is the spin up, N2 is the spin down particle. So total number of particles will be what? For example, 2n. Okay, n1 plus n2 is 2n, which is given, non-interacting spin-off particles. Okay, so so for probability for having to spin-off, probability for having n1 spin-offs, what is the probability? Omega is equal to 2n c n1. Okay, isn't it? So 2n factorial by 2n minus 1 n1 factorial into n1 factorial, isn't it? Yeah. Now, what is the entropy for this? I guess is equal to k ln omega, kb ln omega, k ln 2n factorial by 2n minus n1 factorial into n1 factorial. Okay. Yeah. So if we use Darling's approximation, using Stirling's approximation, what is Stirling's approximation? Ln x factorial is equal to x ln x minus x. Okay, so here if you use kb ln 2n factorial by 2n minus n1 factorial into n1 factorial, that will be kb ln 2n factorial minus ln 2n minus n1 factorial minus ln n1 factorial, isn't it? Okay. So yeah, if I open it, it will be 2n ln 2n minus 2n minus 2n minus n1 ln 2n minus n1 minus 1 is plus 2n minus n1 minus n ln n minus 1 is plus n. So this would have been the expression. So 2n minus 2n cancelled. Right, this is n1, n1, n1. So n1, this one cancelled. Okay, whatever is left, kb 2n ln 2n minus 2n minus n1 ln 2n minus n1 minus n1 ln n1 minus n1 ln n1. So this is the entropy. The question is number of spin-off particle for which entropy of the system is maximum. So this is the spin-off particles probability. So number of which n1 will be maximum. So ds by dn1, because n1 should, like, entropy should be maximum. So d by dn1 of kv 2n ln 2n minus 2n minus n1 ln 2n minus n1 minus n1 ln n1, okay, is equal to 0. So kb goes to that side. This one derivative 0. So this will be n1, wait, n1 2n minus n1 minus 1 minus ln n1 is equal to 0. Isn't it? Is that right? Is that right? So it's kind of if you equate it, it will be, so it will be 2n minus n1 minus n1 minus 2n plus n1 minus ln n1 into 2n minus n1, 0. Let's go to the side. So n1 will cancel out. 2n minus plus ln and 2n minus ln n1. 2n minus n1 is equal to 0. Okay. So It's if you solve this, you will get as n1 is equal to n. Right? So that will be answer. Number of particles will be n. Okay? Is that alright? Yeah? Okay. Next question number 4. Question number 4. A two-dimensional box in a uniform magnetic field. Uniform magnetic field B, okay, contains n by 2 localized spinor particles, localized spinor particles, okay, with magnetic moment mu and n by 2 free spinless particles, n by 2 free spinless particles which do not interact with each other, which do not interact with each other. The average energy of the system at a temperature T is. A 2D box in uniform magnetic field B contains n by 2 localized spinor particles with magnetic moment mu, n by 2 free spinor particles which don't interact with each other. The average energy of the system. So here spinor particles n by 2 free particles which do not interact with each other. So for energy, average energy of n by 2 free spinless particles. N by 2 particles, so n by 2 into 2 by 2 cavity. Why 2 by 2? N by 2 because it's your 2D. Okay, so it's n by 2 cavity. Okay. And average energy of n by 2 spin half part localized spin half particles will be minus n by 2 mu b tan h mu b by kVt. Yeah. So the average energy of the system is not just the addition of the average energy of the system is that E is equal to E1 average plus into average. Okay, kVt minus n by 2 mu v tan h mu v. We have to remember this expression for this one. This one is for n by 2 localized spinor particles. Localized spin half particle. Okay. Yeah. Okay. So this will be this much for this class. We'll be solving more numericals in the upcoming sessions. Okay. Thank you.